Good day, I'm Vincent Saxtetter, and this is the After the Age of Fire channel. This is episode 11, recorded on October 11th, 2025. It's part of a sequence. Uh, the name of this particular episode is Our Energy Harvest. The two previous episodes in this sequence were about the energy that we use, that we consume. Um, and then the last episode in this sequence will be about the balance between the energy that we use and the energy that we obtain every day, every year. So it'll be a 4 episode sequence. I just want to say a word about why you might be interested in pursuing this channel. Um, I went over this in the first episode or two, but I just think it might bear repeating. Essentially, I think we're at a very, very unusual juncture in human history. There's something special has been going on for the last 250 years, having to do with having twice as much of everything every 22 years or so, every generation. And we seem to be coming to the end of that. And so I'm trying to explore exactly where we are in that sequence and what will come next. And so one reason why you might be interested in pursuing this channel is to understand where we are now, um, where the human race is now, and then another reason would be to prepare for the future, to understand what our future will be like and how to prepare for that. And I think that this this content will give you some information and some analysis that you won't hear in other places, and may help you prepare your. I'm not talking about preparing for next year. If you're interested in playing the stock markets or something, then this is not the place for you. But if you're thinking about preparing for the next 20 years or sending your family in a good direction that will see them through the next 50, 100, 200 years, this is the place for you. So it's not exactly a long vision. I'm not talking about thousands of years. I'm talking about decades to up to 100, maybe 200 years. So what will allow your family to thrive, or even to continue to exist, your bloodline, over the next 50, 100, 200 years? Um, Aside from just understanding the world we live in, which I think is interesting enough in its own right. So, in the last 2 episodes, we talked about the energy that we use, and we consume, over and over again, I'll say we consume 46,000 calories per person per day, plus another 15,000 calories in food, fodder, and wood, stuff that's grown and harvested each year. Now, of course, that changes from year to year. So in 2019, it was around 45,800, and in 2023, it's 47,600, a little bit more, but it's still roughly 46,000, so we'll just go with 46,000. And then the food, fodder, and wood, of course, that changes a little bit from year to year. I want to clarify that I'm using, when you talk about the amount of energy that you're using per person per day, of course you have to know how much energy we're using worldwide, and then you have to know how many people there are worldwide. And of course our population, our worldwide population, changes every day, every year. It's over the last 30 40 years, we've been adding about 80 million per year. I expect that to come down soon, but it's been pretty constant, 80 million more total people living per year. That's counting the births minus the deaths, 80 million more. So in order to keep things simple, I've decided in this book, since it's not changing very much each year, 80 million compared to the 8 billion or so on the face of this earth, to just use the 2020 number. And in 2020, our population was about 7.8 billion people, And so whenever I talk about the amount of energy we consume each day, I've divided by 7.8 billion people. So that just simplifies the math a lot and doesn't really change the substance of the discussion. Um, at least over decades, there's a little difference. Um, so, and then I want to say that talk about the breakdown of the 46,000 versus the 15,000 food, fodder, and wood. That food, fodder, and wood includes biomass, in other words, wood that we harvested, chipped, and burnt in electrical generating plants, sometimes shipped around the world to certain generating plants that are supposed to be green. And so we generated around 630 calories that way in 2023, and a bit less, 370 calories in 2019. So not a lot. And then it also includes biofuel. That means basically corn or maybe other grains that we've processed in some factories, and to produce ethanol, which you can mix with gasoline or diesel. And that I'm lumping that in with the 46,000 calories of that's not food, fodder, and wood, because we aren't eating the ethanol and the diesel that we produce that way. So that was 330 calories in 2019 and 400 in 2023. So out of the 46,000 calories or so that's not food, fodder, and wood, that's fuel, about 400 of them are biofuel. And then out of the 15,000 calories of food, fodder, and wood, around 600 of them are what's called biomass, basically chipped, pulped wood, stuff like that, to be burnt in generating plants. So that's just a little bit of explanation. Another thing I should say is I'm everywhere that I give you a figure or whatever, I have it based on uh, some scientific article or some publication of some organization that claims to know this sort of thing, and with what seems to be good reason. So there's an awful lot of backup material that I'm not telling you the names of the authors or the articles or the publication dates or so on. That'll be in the book. But there's an awful lot of material that already I've used, and probably hundreds of footnotes, different articles and publications that already in the first 10 episodes, and there will be a lot more. So I'm not just pulling numbers out of a hat. They're backed up. So let's talk about where we. So this episode is about our energy harvest, where we get our energy from. Okay, and I break it down into 5 categories. One is energy that's not from the sun and not from plants. So since it's not from the sun, all of the plants get their energy from the sun, so certainly not from plants. Then that's a certain amount of energy that we consume. Then there's the energy that we get from the sun, but doesn't go through plants. So we're not harvesting via plants. So those 2 categories together I call them non-plant energy. They don't involve plants. And then the rest is stuff that where plants have a role in harvesting that energy. One category is the old plants, the plants from millions of years ago that generated coal, oil, and gas, and that's where most of our energy consumption comes from today. A 4th category is the plants that grow in the sea. Almost all of that's plankton. That's a way to harvest energy from the sea. And then the 5th category is energy that you can harvest on the land from the sun. So those are the 5 categories, and I think you might be surprised about how much energy we get from each of those categories. So first, the energy that is not from the sun at all, has nothing to do with the sun. Very little of our energy comes in ways that's not from the sun. So basically, there's nuclear energy. We get about 2,060 calories per person per day from nuclear energy. About 850 of that turns into electricity, and 1,210 calories of that turns into waste heat. It's just thrown away, as in just like in any heat-based electrical generating station. So that's one way of getting energy without the sun. Another way that we have of getting energy without the sun is geothermal energy. There are places underground that are hotter than the surface, and so if you can figure out a way to pump to warm something up far underground and then to harvest that heat energy above ground, then you can generate some energy. So we harvest about 100 calories of geothermal energy per person per day worldwide. Of that, around 40 turns into electricity, 60 of that turns into waste heat. So, and then all the other things you can think of, say harvesting energy from the tides or from waves, those are things that well, the waves actually are driven by the sun, but the tides are not. They're driven by the Earth's interaction with the moon, and we get basically zero from either of them. Okay, really zero. If you divide by the 7.8 billion people, it's nothing, literally nothing. Okay, so the total that we get, the total energy that we get without the sun being involved at all, adds up to about 2,200. Almost all of that is nuclear, 2,200 calories per person per day, and of that, about 900 calories turns into electricity, and the rest is waste heat. So overall, it's really not much. 2,000 calories is about the same that you and I and the world eats per day. So, and as you know, we're consuming 46,000 plus 15,000 on average worldwide. So 2,000 is nothing compared to that. So then what about all the energy that comes from the sun but not from plants? And this is what we generally call green energy. And there are three main kinds of green energy. One is hydroelectric power, where you take water that was heated by the sun and was made to evaporate by the sun. It turned into clouds, and then later it rained on the land, but it didn't rain at sea level. It rained at some altitude above sea level, and then as it flows down from wherever it rained to the sea, we capture some of the energy that it has that it picks up by falling that distance from where it rained to the sea. Okay, so that's what hydro is. It's powered by the sun. If there weren't any sun, there wouldn't be any rain, there wouldn't be any clouds. But it's an indirect way of getting energy from the sun. And so we build dams to harvest that energy and so on. Anyway, we get about 1,360 calories per person per day from hydroelectric energy. And that's not changing much, and it will never change, never be much larger than that. We're already harvesting about as large a fraction as you can, as is reasonable, as is possible. There's just not that much energy in the water that falls from the sky to the ground. By the time it hits the ground, there's not much energy left to be picked up, and we're capturing about as much as we can of that energy. Maybe we could possibly double it, but it'll never be more than 2,000 or 3,000 calories per person per day, and it'll probably stay around the same. Then there's wind, okay, and we have been changing the amount of wind that we harvest, wind energy that we harvest quite a bit. From 2019, in 2019 we were harvesting 430 calories per person per day, and now it's 750, so we've almost doubled the number of wind turbines. But still not much. 750 isn't much compared to what we're consuming. Next comes solar, the third of these green energy, supposedly green energy options is solar. That was 220 calories per person per day in 2019, and now in 2023 it was 530 calories per person per day. So it more than doubled during those 4 years. but still not much. Um, Altogether, you take these non-plant energy sources, in other words, ways of harvesting energy from the sun, but not using plants. They're hydro, wind, and solar. They add up to 2,640 calories per person per day, and that's in around 2019. 4 years earlier, it was around 2,000. So they picked up another 600 calories, totaling to 2,600 in 2023. You add to that the energy from nuclear and from geothermal, that comes to 4,800 calories per person per day. And compared to 4 years ago, it's 4,150. So it increased a bit, but not that much. Why not that much? Because hydro and nuclear haven't been increasing much in the last 4 years, and they're not likely to increase anytime soon. We just aren't building enough nuclear power plants to do that, and there isn't enough hydro energy available. So overall, the last few minutes of discussion concerning non-plant energy sources, things that never involved a plant and never will involve a growing plant, no photosynthesis, nothing green, just machines or buildings, installations that we produced. All of these add up, and these are the things that people call green energy. They add up to 4,800 calories per person per day, and compared to our consumption, 46,000 plus 15,000, it's nothing. It's 1/10. So I think I wish I could sing and dance and scream and jump up and down here and spend 2 hours on it, because that's what it's worth, or more than that, because nowadays in the press and in what we learn about how green energy is a huge thing, renewable energy, whatever you want to call it, and there's talk about more and more of it, and there just isn't. There isn't very much of it, and we're building it very slowly compared to the amount that we use. And why we have so little renewable energy and green energy, why we've built so little of it, and why it's so and why we're not building it very quickly is something that I'm going to unpack over the next content. Not today, but it essentially means that whenever you read about nuclear, hydro, wind, solar, geothermal, or any of these energy sources, you're wasting your time, because our energy right now comes from other places, and it's likely to continue coming from other places for the foreseeable future. We have not proven that any of these supposedly green solutions are able to provide for our consumption at the level that we're consuming it, 46,000 calories, okay, per person per day. There's no proof that we can scale up to that level, and so I'm going to spend quite a bit of time in the next episodes analyzing how far could we take these. How much energy could we get from hydro, wind, solar, and nuclear? Well, actually, maybe I won't. Hydro just doesn't have that much. It's very simple to calculate how much gravitational energy you have from dropping water, from water that arrives that rains down on the surface, and then how much energy you could possibly pick up as the water drains from wherever it rains or snows down to the ocean. And it's not hard to figure out that we'll never get much more than that, than what we're getting now. So if I spend any time at all on hydro, it won't be very much, but I will spend quite a bit of time talking about how much we could possibly get from wind, solar, and nuclear in coming episodes. So that leaves 9/10 of our energy consumption comes from plants. Actually, almost all of that, 41,000 in 2019 or 42,000 calories in 2023, comes from coal, oil, and gas. Okay. Around 50 calories, all of it in food, comes from the sea, and then another 15,000 calories comes from the land. So coming up soon, very soon, I think a couple episodes from now, I'm going to talk about the, the bulk of our energy harvest, which is coal, oil, and gas, and whether we can increase the amount that that we get from coal, oil, and gas, and whether we're likely to be able to continue using as much coal, oil, and gas as we are now for very long, or how long we might be able to continue using this amount. Or could we increase it? Could we have used twice as much coal, oil, and gas? Could we use 4 times as much? Remember that we've been doubling the amount that we use every 22 years, so it's a really important question. Are we going to be able to continue our lifestyle of doubling for another 22 years? If we that would involve basically multiplying our coal, oil, and gas by 2, or finding some other way to get it. What are the other ways to get it? They're the renewables, the non-plant sources, which I just discussed. We aren't getting much already, and there's no proof that we'll ever be able to get even the amount that we do consume today, much less twice that amount. And then the other option besides coal, oil, and gas is plant energy harvested by plants in the sea and in the land. So the rest of today's episode will be talking about the energy that we do get from the sea and from the land, how much of it, and why it's the numbers that we have today. So first I'll discuss the sea, which may seem a little disappointing that we're getting only 40 or 50 calories per person per day in seafood, and that's about it, plus some installations on the coasts in the very shallow waters on the coasts. So I'm launching into the sea, how much energy we do get from the sea. And then the other thing that I'll discuss during this episode is the energy that we get from the land, how much there is compared to how much we actually get from the land, and that'll tie up all of our energy sources. I've already told you the final result. It's 4,800 calories from non-plant-based sources. It's 41,000 or so from coal, oil, and gas. It's 40 or 50 calories or so per person per day from the sea, and it's 15,000 from the land. But you might be a little bit curious about how much we can get, how much more we can get, or why we're getting these numbers from these different sources. So today I'll completely nail down the sea, and there won't be much more discussion of the sea in later content. It's basically a hopeless case, and then in later chapters I'll be talking about the energy that we get from the land in more detail, and also I'll be discussing coal, oil, and gas, and nuclear, hydro, nuclear, wind, and solar. So all of those things, but right now I'm just trying to give you the overview so that in the next episode we can talk about how it balances. So I've already given you the numbers. I could discuss the balance right now, but I think it's good to give you some explanation, a little bit of explanation about the sea and about the land. So the sea, we should start with, since almost all of the energy on offer for the human race comes from the sun, and that comes down on the surface area, either of the land or the sea, we have to talk about how much surface area each person has, if we were to divide the world equally between all of us. So if you did divide the world equally between every human being, we would each have a square that's 260 meters on a side. So 260 meters wide and 260 meters long. I guess that's around the same number of yards long and wide. And more than two-thirds of that would be ocean. So, and as you can imagine, quite a bit of sunlight hits that our share of each person's share of the ocean. So if you could harvest all of that sunlight that hits the ocean, you would get a lot. of energy, but the problem is that it's very difficult to harvest energy at all from the ocean, and I'll come to why. The first problem is that the ocean is a desert. You can see it easily enough. It's blue, not green. If it weren't a desert, it would be green. It would be colored green like forests and like fields are. The plants that photosynthesize are all green, but the ocean is blue, and that means that in most of the ocean, nothing or almost nothing is growing. And why is almost nothing growing in the ocean? Well, plants need four things to grow. They need carbon dioxide and water. Well, there's plenty of carbon dioxide and water in the ocean. Okay, and then they need sunlight and they need nutrients. Uh, Things like phosphate and sulfur. Um, the things that actually, if you take a dry plant, say a piece of wood, and you burn it, the ashes are the nutrients that went into that plant. So um, that's what plants need. And the problem is that in the ocean, you don't combine nutrients and sunlight in the same place. The sunlight all is at the top 200 meters of the ocean, and then there's enough murkiness, enough dirt in the ocean that the sunlight doesn't make it far down. The ocean is on average more than 3,000 meters deep, so only a thin layer, so to speak, thin layer meaning 200 meters or so of the top of the ocean has sunlight. Okay, so that's where things could grow just based on sunlight, but that top layer needs nutrients too, or else nothing will grow. Okay, and the problem is that when you dump nutrients in the top of the ocean, they begin to fall. Okay, and they fall fast enough that pretty soon most of them are past no, all of them are past the top 200 meters and down in the dark zone. So you have sunlight in the top 200 meters, but the nutrients are all far below that. And that's why things don't grow in the ocean. It's just very simple. Now, you don't have the right combination of sunlight in the same place as nutrients. So however, there are oases in the ocean. Okay, what are the oases? Well, one kind of oasis is called an upwelling. It's a place where deep ocean waters are moved by ocean currents upward toward the surface of the ocean, and that's not a large percentage of the ocean, but where there are upwellings, it's really, you get extraordinary amounts of sea life. There's some near the equator. There's some at certain points along the coasts. And the other way to get an oasis is what's called continental shelf. The world's continents don't stop where the water starts. They keep going, descending very slowly in places. Sometimes they keep going 200 kilometers out from the beach. The water might still be only 50 meters deep or 100 meters deep, because the continent actually goes that far in places, sometimes several hundred kilometers out from the beach. In other places, you drop off pretty quickly within a few kilometers. You're hundreds of meters or thousands of meters deep, but in some places the continent just keeps going for quite a while. And these places, so some examples are like one is the Grand Banks off of the northeast seaboard of the United States. Another one is the North Sea between Scandinavia and the UK and Germany. Another one is the Yellow Sea between China and Korea, or on the other side of Korea, there's a lot of this continental shelf between Korea and Japan. There's also places around Arabia, around the Middle East, and these places are great for fishing. Why are they so good at why is continental shelf so good for growing things? It's because all of the water down to the seafloor it is sunlit, and because the seafloor is only 50 or 100 or 200 meters deep. Okay, then you come to the edge of the continental shelf, and suddenly it drops off and goes down to the normal ocean depth, which is several kilometers, 3, 5, 6 or more kilometers deep. So all the nutrients on the continental shelf are trapped there in the sunlight, and so you get the right combination of nutrients and sunlight, and so you get lots of plankton, and so you get lots of fish and other sea life. So these are the oases. You have continental shelf and you have upwellings, but these between continental shelf and upwellings, these only cover a small fraction of the ocean. Okay, that fraction is extraordinarily productive, but most of the ocean is not. And more than 9/10 of the ocean is not productive. It's desert. So taking the ocean altogether, if you count how much sunlight is being captured by the ocean's plankton, by its plants, and you compare that to how much sunlight is being captured and harvested by all the plants that live on the Earth's land, the ocean actually harvests a little bit less, even though it has more than twice or close to 3 times as much area as the land does. So one immediate lesson from that is that even if we could harvest all the energy that's available from the sea's plants, we could at most double our harvest from the land. I mean, the sea is actually harvesting a little less. Its plants are actually harvesting a little less than the land's plants. So even if we could go to sea and farm the way that we do on land and so on, which we can't, we could at most double our harvest. So compare what we're used to doubling every 22 years. We won't get. This could at most keep us going for another 22 years, not for another century or anything. So then I want to talk about another problem with the sea. Why is it that even though its plankton harvest the same amount of energy as land's plants do, why is it that we're only able to get 40 or 50 calories per person from the sea while we get many thousands from the land? And the main problem with the sea is that it's made out of water. Water weighs, you take say a liter of water and you compare that to how much air fits in that same liter container, and the air in that liter container weighs just over a gram. So water weighs almost 1,000 times more than air does. And as you know, if you're out in a storm or even in even a little bit of a windy day, the air can blow you around, and it can do interesting things to dwellings or to cars, or it can also rip away all the topsoil if you give it a chance. It can really affect your life. Okay, and then you have water, and water is so much heavier that it can, you really can't fight it. The question here isn't whether you could build a pier or a ship or something to go in the water. The question is whether the cost of doing that, the cost in energy of building something to deal with water, with seawater specifically, wouldn't overwhelm whatever energy harvest you could get from the sea. So the question is, can you break even? Can a plant break even? Can it harvest as much energy as it's expending to deal with the sea and with the tremendous stresses that it has with the water trying to tear it apart all the time? Not just plants, but anything that we might build. Can we build anything at a cost, at an energy cost that's less than the amount of energy that that thing is likely to harvest? And the question with the answer for the sea is no. The only way to make a profit in the sea is to go with the flow. You have to let the sea take you where it will, and you have to be where it's so small that the sea doesn't rip you apart. How small? The answer is very, very easy. The only thing that grows in the sea is plankton. It's one-celled organisms. So you have to be as small as a cell before you can make a profit from sunlight in the sea. Anything bigger than a single cell will spend more energy keeping itself together than it gets from sunlight. You understand I'm talking about harvesting directly from sunlight. I'm not talking about animals, right? Animals have a different way of getting energy. Sea animals do. They're able to prey on plankton or on other sea animals, and so they can get energy more quickly, and that affords them the ability to keep themselves together, and even whales together, and fight the flow, fight the water, and keep themselves from being ripped apart. But a plant can't. A plant has to get its energy directly from the sun. That's the definition of a plant, and the sun comes down in a certain quantity per square meter, and the plant has to capture that sun somehow and keep itself together. The only way it can do that, it works out so that the only way it can do that is by being a single cell of plankton. Okay. And the problem for us is that even though the world's plankton harvest about the same amount, just a little less energy than the world's land plants do from the sun, we're unable to eat them or turn them into anything useful. The problem is, well, first of all, they are microscopic, useless for our food or pretty much anything else, and very hard to harvest. Another one is that they're moving all the time. That's unlike our plants, which we plant them, they stay put for several months until it's time to harvest the corn or whatever. And also they live days to a week, maybe a week. Okay, so you have to be. It's just useless. So we really can't harvest plankton. So we have to harvest something further up the food chain, and of course, since you're further up the food chain, you get less of the energy. A lot of the energy is expended as it goes from whatever's eaten up to whatever's eating it, and then up another level and another level. Okay, and it appears that we're eating pretty much as much. We're harvesting as pretty much as much as we can from the ocean right now. We continue to put more and more trawlers, boats in the sea, more and more equipment and more technology for finding fish or whatever, and our seafood harvests continue to go down. This has been going on for decades. The harvest going down has been going on for decades. Our increasing equipment has been going on for centuries, and we've maxed out the sea sometime in the last 50 years. We just aren't getting any more from it than we did before, even though we're spending more and more on it. So how much do we get? We get about, if you divide by the number of persons on the face of the earth, it's about 34 grams of seafood per person per day. That's 2/3 of a large egg, or 40 or 50 calories. More than half of the fish that we eat today is grown in farms, it's not being fed by the sea. So given that we're spending more and more on harvesting from the sea and we're getting less and less, that's a sign that we've maxed out and we'll never get more than 40 or 50 calories per person per day. And I just explained why. It's because the sea is a desert and because we have to eat high up the food chain. There is one possibility where we could get a little more. There's a very small shrimp that weigh 1 or 2 grams. They're called krill, and they're the most abundant sort of in terms of mass, they're the most abundant sort of animal, bigger than plankton. And if we could capture all the world's krill every year, and they kept growing back, then we could get somewhere around 250, maybe 200 calories per person per day by eating krill. Now, certain countries do already eat a little bit of krill, but nothing compared to the quantity that actually grows out there especially in the upwellings and sometimes on the continental shelf probably, but certainly in the upwellings. That's where the whales go, for instance, to capture their food. So we could edge out all the other animals that live on krill, and we would get 250 calories per person per day from the krill, which is still a few percent, maybe 1/25 of our total harvest of grain from the land. So that's the most you could imagine getting from the sea, from the sea's animals. 250 calories at the cost of innumerable other species. And that's only if we got all the krill. So practically speaking, the best we could do is still a very small fraction of the energy that we get from the land's plants, and there's really no point. So given that we can't get any more energy from the sea's plankton and plants and animals, what about using other ways of getting energy from the sea, mechanical ones? Okay, so we could think of wind turbines. You build wind turbines in the sea, or how about water turbines underwater that harvest energy from the ocean currents? Maybe you could make solar panels that float on the surface of the sea, or maybe you could try to make farms at sea by walling in certain tracts of water, making walls around it so that then you could fertilize whatever's inside of that tract of water. So you'd make it, there'd have to be a bottom to the tract, and I don't know whether you would try to do it using solid things, sheets of metal or something, or whether you would use something like fabrics or something flexible. Anyway, you can imagine trying to farm at sea that way. The key is you'd have to be able to keep a certain tract of seawater in place, not having it leak very much, so you could fertilize it so it could actually grow something for you. Okay, well, none of these work. None of these will break even. They can harvest energy, but they'll never break even. You'll be spending more energy on them than you get out. Okay, let's talk about wind turbines. Okay, so we do build wind turbines at sea. Okay, and we need to build them cheaply so that we can break even. And right now we build them at up to 30 meters depth, seas that are deep, whose depth is up to 30 meters. So that's very shallow continental shelf. It's 1/100th of the average depth of the sea. It's a very small fraction of the sea. And the way we do that is we take a large steel tube, large meters wide, and we and we take it and we pound it like a nail into the seabed. And once we pound it into the seabed, hammered it into the seabed so it's stuck there, then we take the actual wind turbine and we put it on top of that tube. And so that's called a monopile. We can build monopiles in seas at depths of up to 30 meters. And we could imagine building other structures at depths of up to 60 meters. Beyond 60 meters, that's just not in sight anytime soon. That's going to work. So if we did figure out how to build wind turbines at economical prices in seas up to 60 meters, then that might be roughly 10%. The amount of sea that we'd be able to access that way would be roughly 1/10 of the world's land area. That's the seas of depths up to 60 meters, 1/10 of the world's land area. So you can imagine that we aren't going to get much more energy from wind if we build at sea than we would if we just built on land. Now the winds at sea are a little faster, so you get a little more energy. So maybe you could increase your energy, your wind energy harvest by 20%. I've worked at that. I'll talk about that a little bit more in a later episode. Maybe you could harvest 13,000 calories per person per day if you spent enough money building wind turbines at sea. So it's nothing like the amount of energy that we consume. In general, if you want to get energy from the sea, you need to build it in shallow water. There just isn't that much shallow water compared to the world's land area, so you'll never get that much compared to the world's land harvest. If you want to go deeper, then you have to deal with the sea on its own terms, and the structure must be able to hold its own against the water. It must be strong, resilient, durable. It must be able to endure corrosion. You must be able to construct that structure at sea, or else build it on land and port it out to sea, as is done with some oil platforms. Because the average depth of the sea is 3,680 meters, the thing must be able to function without any anchor or any foundation. That means it has to be able to go wherever the sea takes it. You can't have motors on it to keep it in place because you'll spend more money, you'll spend more energy trying to keep the structure in place with those motors than you are able to harvest from the sun. So no motors floating adrift. It has to endure corrosion. It has to endure fouling from all sorts of organisms that like to grow on anything that's around. Anything solid in the sea will attract organisms. And then there's the danger of visiting this structure, maintaining it, building it in the first place, maintaining it, and then that danger is multiplied whenever you need to go underwater. So you just aren't going to break even this way. We can talk about how much energy, how bad this break-even problem is by talking about oil wells. We do harvest some energy at sea, oil and gas, okay, and we harvest. I want to compare to the amount that we need to break even on land. On land, you can break even from an oil well if an oil well will keep it open. The U.S., for instance, keeps 700,000 oil wells open that harvest 10 barrels per day. That's 10 barrels per day means 15 million calories per day. So 15 million calories per day, enough to keep 70 Americans going, or 300 normal average people going. That's enough to keep one oil well going in the U.S. On land. 15 million calories, 10 barrels. On the other hand, the oil platforms that we build at sea are 10,000 times bigger in terms of the amount of energy that they capture. So a typical oil platform might capture 100,000 barrels per day compared to 10. Okay, so unless it captures somewhere in the range of 100,000, it's just not worth it. We're not breaking even. We never will, so we don't build them. Okay, so for comparison, that amount of energy, the amount of energy that a typical oil platform harvests, is the same as a square of prime farmland 100% farmed, it's 150 kilometers on a side, or it's the same as 7,000 wind turbines, or it's the same as 6 nuclear reactors. That's the amount of energy. So you have to be able to somehow, at the same price as a single wind turbine, harvest the same amount of sunlight as a square 115 kilometers on a side. From in the sea. So that means you basically have to build a structure that's more than 100 kilometers on its side at the same price as a single oil platform. And you have to maintain it and so on. It's never going to happen. We're wrong by, the imbalance is wrong by a factor of 10,000. So overall, the only way to get energy from the sea is to build in very shallow waters, say 60 meters deep or less, or else to catch seafood, which currently gives us 50 calories or so. Now, I want to finish with a few words on our harvest at land. So, as you know, we get 15,000 calories per person per day from land, and I want to talk about the breakdown of those 15,000 calories. So first of all, you divide the world's land among us all evenly. That's a square for each of us that's 130 meters on a side. So not shabby. If we each had, of course, that's some of that will be desert, some of that will be mountains, some of it will be farmland, and so on. So 130 meters on a side, or a total of 16,700 square meters per person. I forget what that is in acres. It's a few acres per person. Now, 1 square meter of the world's land or sea, if you're counting the land and everything above the land, receives 7,000 calories per day from the sun, on average, averaging north to south and so on. Now, 2,000 of that 7,000 is reflected immediately into space. That's why you can see the Earth when you're in space. Another 1,700 is absorbed by the air and by the clouds. Okay, so that leaves 3,300 calories per square meter that arrives at the Earth's surface. Per square meter, 3,300 calories in a day arrive at every square meter of the world's surface, well, averaged across the world. Now, talking about habitable, the regions where people actually live, okay, in habitable regions, the average is 4,000 calories per person per day, because we tend to live closer to the equator than to the poles. And the range is typically between 2,700 calories per person per day and 5,300. So the high end of the range is roughly twice the low end of the range. So between 3,000 and 5,000. And in deserts, it's a little bit high. In deserts, the amount of calories arriving at a square meter is typically between 5,000 and 6,300. Okay. Now, so maybe just to boil that down, the typical amount in unhabitable land is 4,000 calories per person, per square meter per day. Now, a little less than half of that goes to evaporating water. I'm not talking about heating the water. I'm just talking about whether or not water's at the boiling point or whatever. Just to get it to turn from water into air vapor, into vapor in the air, costs a lot of energy. Water just sucks up energy like you wouldn't believe, and so to evaporate all the water that gets put in the air uses about half of those 4,000 calories. So, and then there's also the energy that's spent heating up the water and so on. So a lot of the energy coming from the sun, it goes into making water turn into water vapor, thereby fueling the rain and the snow and so on. So suppose we harvested every one of those 3,000 calories per square meter per day, and each of us has 16,000 some square meters, then each of us would have 60 million calories per person per day. So that sounds like a lot, 60 million. That's more than 1,000 times what we're actually using. We're using 46,000. It's 300 times what the United States is using per person. It seems like a lot. But it's actually not a lot, because you can recall that from 1700 to 2014, in other words, the previous three centuries, we multiplied our energy consumption by 6,000. Okay, and we only have a factor of 1,300 to go more until we consume every single calorie that's arriving at the Earth, at the Earth's land area. So if we could do that, if we could harvest every calorie that arrives on the Earth's land, and if we continued to multiply our consumption by 2 every 22 years the way we have been, then we would hit our limit in about 200 years. So that's a very obvious limit. There's no way that we'll still be multiplying our consumption 200 years from now. Just absolutely impossible. There's not enough sunlight. But there's a fly in the ointment there. Actually, for every 345 calories of sunlight that arrive on the Earth's surface, only one gets harvested by the land's plants. They only get 1 out of 345 calories. Or another way of saying that is that land's plants harvest 170,000 calories per person per day. So suddenly that's only 3 times larger than the average amount that we're using per person per day, and it's actually smaller than the amount that the United States and some other rich countries are using per person per day. So if we do not succeed in multiplying the land plant's harvests, we are already very close to our limit, even if we were to use every single plant for our own purposes. Okay. Now, out of those 170,000 calories per person per day that the land's plants harvest, we get 15,000. Well, how's that work? Well, there's the croplands and pastures, the ones that we dedicate to being pastures or croplands. Those could harvest 64,000 calories if we left them alone per person per day, but we don't leave them alone. We cut them down every season or every year, and therefore, because the plants are not growing in the way that they would by themselves, they actually get less. They get 46,000 calories per person per day. Most of those 46,000 calories are left in the soil. They feed like their roots and their stalks and their leaves that are no use to us, or they feed the bacteria and so on underneath the soil. We get 9,000 calories from our croplands and pastures. And then from all the other land, all the things that are not pastures and cropland, we still send animals into those land to eat things, and we still log them, and we get another 6,000 calories from there. So 9,000 from the pieces of land that are under our close management, and another 6,000 from other land, for a total of 15,000. So lastly, what do we do with these 15,000 that we do get from the land's plants? Well, 6,000 calories is sort of roughly, so I'll break it into 6,000 and 9,000. So 6,000 is 2,700 end up on our table. 2,400 is wood products that we use, and another 1,000 is the biofuel and biomass that we burn in our vehicles and in our electrical generating plants. Then there's another 9,000 calories that, where does that go? It's I'm not sure of the exact number, but quite a bit of it, somewhere between 1,000 and 3,000 calories. I'll put my guess at 1,500 calories is food waste. So this is food that we never get around to harvesting, or we let rot after we harvest, or we process it and then we throw away the contents of whatever we processed, or it ends up in a restaurant or on our table in a grocery store and then never gets eaten, never gets bought, whatever. There's an awful lot of that, and may be equal to the amount that we eat every day. So let's say 1,500 of that is food waste, and then another around 7,500 is fodder for our animals. Now, we feed our animals somewhere around 7,500 calories per person per day, and we get back 800 calories from them in eggs and milk and in meat, cheese, animal products. So they give us back around 1/10 of what we put into them, what we give them. So there's 16 million calories per person per day arriving at the land. Okay, of those, 170,000 calories per person per day are getting harvested by the land's plants. Out of those 170,000, we're getting 15,000 calories per person per day, and we choose to spend a lot of that for our animals, 7,500, and get back 800, about 1/10. We also choose to waste somewhere 1,500 or more calories per person per day that just gets thrown away. And then the rest goes to things that are actually useful to us: food on our table, wood products, biofuel, and biomass, around 6,000 calories there. And then if you count the 800 calories from the animals, that would add up to around 7,000. So is there any way that we can get better than that? So can we get better than 15,000? Could we get closer to 170,000 from the land's plants? Could we get better than 670,000? Somewhere in the range, closer in the millions, since there's 60 million calories on offer from the sun. Well, I'll discuss this in some detail in later episodes, and that'll be the material of future episodes. Okay, with that, that's our breakdown. So 15,000 calories from the land's plants, 50 from the sea, 4,800 from non-plant-based sources, and 41,000 from coal, oil, and gas. And we'll talk more about whether we can get more energy from any of those, or but the next episode will be about the balance and how the balance works out. So keep coming back. Thanks for your attention, and have a good day.